Hello. Yes, this is a very strange start. Hang on. This is all screwed up. Sorry. Hang on. Right as that was happening. Okay. This is a picture of everything going wrong. Oh, good morning, everybody. So what happened was just before going live, or just before stream time, I powered up I had the laptop running, which has OBS, and it does my Stream Deck stuff, and Companion to do all of the scripting for the different things. And what is going on with this? Yeah. And it wasn't working. So I ended up creating, what was I doing? I ended up having to restart Companion, restarted OBS. I had to change the network settings on my laptop because it couldn't connect to the ATEM. And then I started the stream and the script failed to change the scene. It normally goes to a little 60-second video clip, which is the countdown, and it failed. Anyway, it all went wrong. But the timer started, which meant that by the time I switched to it, yes, you did order extra squirrel with your coffee, Crispian. That is right. And because of all of this thing screwing up right before I started, I have not even OXRS. I have not even opened the text-to-speech thing. Oh, which is giving me a bad gateway. Oh well. So I don't have text-to-speech. That means I'm going to have to do this the old-fashioned way, just using my brain, and we know how dangerous that is. So good morning to Crispian, Stephen W, Gerald 42, Stephen W again, Gerald 42 again, Wagon Loads, Michael. I think we have several Michaels. That's Michael Wires. Amanda. Amanda says, hot drink in hand and breakfast done. I'm now ready for me to start. Okay. Where are we? John Whips. Midnight snacks to hand ready. So you're in an unfortunate time zone. Imi is here. Tabraze. Simon R. Simon's messages retracted. What did Simon say? Russell Rainey. Luminator. Mitchell. Okay, yep. So Mitchell said text-to-speech system is offline today for system upgrades. David Howes is here. Gavin, good morning, Gavin. Scott, Jack's Tech. Just scrolling down. Have I missed anybody yet? John Whips, Wagon Loads, Cassio, Tech Nebulous, Mitch. Hey, good morning. Sorry, that sounded like knocking. Lachlan, right at this moment, has conscripted his family to help him, and they are laying new carpet in the office next door. And so there are sounds and things coming through. I just thought that was someone knocking on my door, but it's not. It's someone with a hammer. Scott. Did I say hello to Scott? I don't know. Anyway. All right. Before I forget, because my brain has just been scattered in many different directions, I've got to do the important thing. I acknowledge the traditional owners of this land, the Whadjuk Noongar peoples. I pay my respects to their elders, past and present, and to Aboriginal elders and peoples from other communities who may be taking part in this live stream today. We got Clinton as well. And yes, okay. All right, I will close off the thing for the portal because that is not being a thing at the moment. Now, I don't know if you can hear it, but there is a... hang on, I'm going to bring something up on the screen here and do... No, before I do that, I'm going to separate off that tab in the browser, and I'm going to hide this one, and then I'm going to do this. Okay, so as you can see, the 3D printer is running right now. It's making these little standoffs. These are standoffs for the test modules that go in the Testomatic. Okay, A bunch of updates. Because I didn't stream last weekend, I've got that time blindness thing. Was it last weekend that I didn't stream? I think it was. I think it was that I wasn't. So it's 2 weeks since I've streamed, and since then there's been a lot of progress on the mechanical aspects of Testomatic. So what you can see printing here are a couple of 16mm spacers. Yes, yes. Thanks, Amanda. A couple of 16mm spacers, and you are about to see them in use and the reason for them. This is part of the structure of the module that sits in the top of the Testomatic and provides the mechanical and electrical connections to the device under test. So GitHub, okay, and for those who are interested, a couple of weeks ago, I can't remember who it was, someone asked me to update the Testomatic repo because they wanted to look at this as a potential thing to use in their workplace. So last weekend I did some updates and added a whole lot more explanation. This repo is now far more useful. Standoff for Gandalf? Wagon loads? I don't get it. What? Okay, so I am going to do my best to keep this repo updated. Oh, that's the sound of a happy 3D printer finishing its job. So I'll go and grab those standoffs in a moment and we'll put them in place. Yeah, so I added some more information such as the design goals behind this, and I've had conversations with quite a few people about Testomatic over the last couple of months, and the way this is basically a summary of the way that I try to explain it to people and the goals, what I'm trying to achieve with this project. And yeah, when I started writing this down, I realized that it came down to 4 things. One of which is minimize reinvention. I don't want to have to start from scratch every single time I want to build a tester. The second is, and this came out of a conversation I had with Mitch, is to provide enough built-in I/O to make the majority of tests easy, but with expandability to make harder tests possible. And that is mostly Mitch's phrasing, the way he described that. I described it in a slightly more long-winded way. And the thing is that with all the different devices that you need to test, you can't allow for every single possible thing in the test framework. There is always going to be some edge case that you haven't thought of. So I just need to cover all the basics with some digital I/O, some analog inputs, analog outputs, and then the rest of it can be handled by special purpose devices on USB, SPI, or I2C. So those 3 things are also brought up to the test module. So you can expand it and do whatever you like. So allow the chassis to be quickly reused for multiple device under test, with each device under test having its own test module. I want to be able to just unplug a module, plug a different one in, and I'm good to go for testing a new type of PCB. And fourthly, integration with an external test management logging platform for centralized storage of test results from 1 or more testers. Because you've got to think about, what are you going to do? Excuse me. A lot of the time it's enough to just test a board and get a thumbs up or a thumbs down. You get a red or a green, and hopefully if you get a red, you get some information, some diagnostics out of it that tell you why the device failed, so that you can then go off and rework it. You can fix whatever needs to be done, test it again, and then get a pass condition. But ideally, you want to actually record that information. And if you've got multiple test units, you need to be able to collate information from multiple test units. So, I just saw Scott said, you missed point 5, easy enough for a squirrel to operate. Oh, and good morning, Don S. And Wagon Load says, do you have a KiCad version of Testomatic? No, I don't. However, the Fusion Yeah, at some point I wanted to convert this and make it a native KiCad project. At the moment it's being done in Fusion 360, and in the repo, if you go into hardware, the version 2 board and schematic files are here in Eagle format, because I've exported them from Fusion in Eagle format, and you can then you can open those in KiCad, or there's an import or something that'll bring them into KiCad. That's not a perfect solution. It'd be nicer if it was native KiCad, and at some point I'm going to do that conversion and then just start working on it in KiCad, but not yet. Yeah, so storage of results. So it's just a little explanation here of the thing. There's a photo of the first version, which I've been using for a little while now, and this has been used to flash firmware onto many boards. And then there's a photo of the version 2 thing, which is what we're going to be playing with today. And you can see there is the vertically mounted Testomatic PCB. Over here is the module, and that's actually the first thing we're going to look at. There's a touchscreen on here. In the bottom is the Raspberry Pi. There's a power connector on the back, so power can come in from something like a lab power supply. There's a power switch on the back with an LED in it. Kind of cool. The power loom comes through, plugs into the Testomatic PCB, and you can see the edge connector up the top here to link through to the test breakout. So there's some info here about the Testomatic PCB, and I've already started some revisions for v2.1, although those revisions may not be necessary after something that I have just done in like this morning. We're about to find out, and that is why the printer was running. All of this will start to make sense. Scott says, one day John will wean himself off bad software. Yep. Alistair, good morning. Yeah, so there is a clearance issue with this USB connector. This thing right in the middle here, this is a problem, or it has been a problem, and I think I've just resolved that problem with a mechanical change. That's why the 3D printer was running. So this is showing the overall structure, the test module, as a view kind of from underneath, so you can see it as this is where the different parts of the system sit relative to each other, with the case invisible. So there's the laser cut enclosure that holds all of this together, but you can't see it in that view, and it's not showing all the wires and things, but this is the major elements of the system. And then there is the test pin carrier board, which is the PCB that makes up part of the test module. I've got information here about features and expansion options. I'm going to get to this in a minute because we're going to look at this. I've just been messing around with this. That's it, I think. Oh yeah, here. I actually set it down here in the... Oh no, I need to edit the README. There's an extra full stop. That's no good. Yeah, so down here, created in Fusion 360, exported as Eagle, which can be imported into Fusion 360 or various other packages, including KiCad. Yes. Alrighty. That is... So we are done on the print. Okay, I am going to go and grab that off the printer. Peter says, too many full stops are never enough. Stephen says a CM4 would have also resolved having to have a USB cable. I think that would have given me other problems, because with a CM4 I would then have to implement Ethernet, multiple USB ports. I'm using all 4 USB ports at the moment, and I really need more. And anyway, you will see that in just a moment. So I've got a hub built into it. In fact, I've got a 4-port hub built into the Testomatic, and then I've got another hub in the back because we need to plug in a lot of peripherals. What am I doing? What am I doing? I don't know. All right, I'm going to grab the things off the printer. Here we go. Little standoffs and overhead. Okay. slide on over here. Yeah, what you're looking at right now is you're looking down. I'll move the microscope out of the way a little bit. You are looking down on the Testomatic V2, and there are some cable management things that need to be resolved, but it is coming together, and it's almost like the render. So we've got the XT60 connector in the back there, we've got the power switch, the loom that goes through. Like if you look at this, and yeah, the Raspberry Pi sitting in the bottom. If you look at that, and you look at, where are we? Look at that, it is actually kind of close to the same thing, apart from not having this USB hub. Hang on, I've got a cough. Stephen W says, Ethernet on a CM4 is trivial, just a mag jack and 10 traces. Yes, but why should I do that when I can just use a Raspberry Pi? Okay. Yeah, so we've got the IDC cable here going from the Pi across to the Testomatic PCB. The focus is a bit hard because of the depth of field issue. It's focused down here on the bench. Something's rattling. What was rattling? I don't know. Something's rattling. Okay, so onto the module. Let's start with the module. And in fact, I'm going to explain. Yes. All right. Let's look at this problem. How am I going to show this? Now, when I did the oh, I know what I can do. Where is it? Test fixtures. There. I have here the equivalent test fixture to this for Testomatic V1. So this is the Testomatic V1 test fixture for that same target board. And what you can see is, so we've got, well, this one's upside down. It's meant to be like that, but you can see we've got here the test fixture for Testomatic version 1, and it's got the IDC connectors along the front here. So that is how I was connecting through to the version 1 breakout. Plug in the IDC headers. And what you can see is that this is quite thin. How thin? I don't know. How thin? 20-ish millimeters, give or take. So, but this one has the test pins soldered directly to the test pin carrier board. So this PCB here. The problem with that is that these can fail with use because they get lateral pressure on them, they break, they wear out. If you're testing thousands of boards, you need to be able to replace them. So the new version, this one, uses test pin sockets. And this is why I had my clearance problems. Where are the sockets? Where are the sockets? Got some here somewhere. Yes, here we go. Okay. Here are test pin sockets. I'll find one that was opened. Yes, this one. And actually, I'll chuck this under the microscope. That'll make it easier to see. There and there. Where's the view? Where? I've got to find the spot for the microscope. Got to find it. There. Microscope zoomed in too far. Let's zoom out. Okay, now the test pin socket that you can see here, this is the socket end, just there. That is where the test probe plugs in. You can see a little bulge around it here. So there's a ridge around the socket. That is a depth guide. So when this goes into the carrier PCB, it slides in from above and then it stops against this little ridge. So that controls how far this sits down into the PCB. And you can get these with different distances here. So that gap there can be different, and that allows you to control the height of the test pins. And you can have test pins at different heights for things like making sure that your ground connection connects first by having those pins slightly higher, or allowing clearance for pins that need to go onto the bottom of populated pins because the connectors need to be lower. So that is the height guide for the test pin socket. Now, this is the critical bit. You see this part on the back here? This is a pin sticking out. This is actually intended for plugging into a DuPont cable. And I know I don't really like using the term DuPont cable, but that's what everybody calls them. Like, I've just got to shuffle through here. Here we go. Here's one. So this sort of thing. It's the microscope is not the best way to do this, but you know, these sorts of cables, this sort of cable where it's got a socket, and what you can do is when all of your test pin sockets are mounted, what you do is just plug a DuPont cable onto the bottom. That's the reason, I'm going to switch back to overhead view. So that is, where are we? Here. That's the reason that these sockets have this pin sticking out the end. And the pin is quite long, but it's designed to plug into a cable. And then this cable goes to your tester, whatever is running your tests. And you end up with a big mess of wires coming off these, but it means that you can unplug them if you need to, reconfigure them. You can get these with or without this pin sticking off the end. And having the pin obviously makes it longer. So in this case it is, how long? Yeah, close to 8 millimeters, oops, of extra length from that pin sticking out the end. Now that is a very important element in our story, because this is getting to the point of all of this. I'll just put this other stuff out of the way. And why I've just changed stuff in the last day or so. So this is the version 2 test module, and these test pins are mounted in sockets. They're not directly soldered to the PCB. And the sockets, as you can see, protrude through the back. They come through quite a long distance. And up until about half an hour ago, these, these sockets had the pin sticking off the end, which took them down to about here. It added that, 7 or 8 millimeters that we were seeing before. And so what I had was these spaces on here, and then, where is it? This base plate was on the spaces, and it made the whole thing too deep. So what I'm going to do now is, if I can find, yep, all right, I'm going to do a little job here while we talk. Never seen a screw-in pogo pin though. I need a screen just in front of me here so that I can see the chat. Steve and Steph have been storing Acons, rattling always equals infernally lost screws. CM4 has USB. I was able to power my Pi from the same USB hub that I was using to expand USB ports to the Pi. Oh, Austin! Austin's here! Fantastic. What else is going on in chat? How would the CM4 talk? So Austin says, was making my milkshake late because I was fixing my 12-volt compressor while working on my new car and first car. Awesome. You got a new car, Austin. That's cool. Please tell me more if you don't mind sharing. I know you've been, so for those of you who don't know, Austin does really cool bike projects. Now, what else is in chat? We're in Great in Sydney. Close the bag. Wagonlight says if the test pin would screw into the socket, you could manually dial in the height of the test pin. Oh, that's an interesting idea. Yeah, I wonder if there is some way of adjusting the height of the test pins. Now, for those of you who wonder what's going on, what am I actually doing right now? What happened was I printed some 15mm standoffs about an hour ago, this morning when I came in, and then discovered that 15mm was not quite enough to clear these test pins. So what I then did was print 16mm standoffs, and hopefully that will be just enough. So it looks like I'm just taking off a standoff and replacing it with another one the same size, but in fact it's going from, I'm taking off 15mm standoffs and putting 16mm in its place. And this should get us to where we want to be, I hope. All right, so now I should be able to, where is it? Oh, that way, and then that, and that should no longer scrape. Doesn't, it feels good. I think that should no longer scrape on the bottoms. It should just clear, and it looks like it does. Got nice clearance from all of the pins. All right, so now I know that I need a 16mm standoff for this base plate. And you can see that up near the top, there's some Sharpie on there. I was marking that up because my plan had been to come in this morning and cut a notch out of that as extra clearance for the USB cable. And in just a second, once this is assembled, I'll put it into the chassis, and then you'll see why that is a problem, or why it was a problem. And I think the problem is now solved, and I think I'd no longer need to revise the Testomatic PCB because the location of that socket, that USB socket, will now be below the height of the test module. All right, there we go. One test module fully assembled, and it's now thinner than it was before because it used to have these 25mm standoffs, and it now clears, it just barely clears the sockets for the test pins. Actually, out of curiosity, how thick is this now? Okay, it's about 30mm thick, not counting screw head sticking up or the little rubber feet that I've put on the bottom. All right, so that's one of my goals with the design of these modules, was to make them reasonably robust and possibly stackable, so I could sit them on top of each other without any damage. And so I've got the backing plate which protects everything. So with some rubber feet on here, it means you can just put it down on a bench. It's quite robust. There is no edge where it's going to take any damage, and the test pins are contained within the height of the top plate, which means you can even just put it down upside down and you're not going to damage any test pins. So part of my goal was to make a module that is fairly robust and doesn't have any delicate parts that are protruding outside of the mechanical structure. And even the edge connector there is contained within the cover. So the plastic cover, or the acrylic cover, comes over the edge there and protects it. And then you can see the LEDs there. It's got power LEDs for the 3 power rails going to the device under test, and 5V and 3V3, which are the tester power rails. And there is the EEPROM for identifying the module. So we can plug the module in and identify it from the EEPROM. So that's the old style test module. This is the new style. Okay, so clearance. How am I going to show this? I might have to adjust the focus. But what you might be able to see here, see this cable, this black one. This is a USB cable that is plugged into the vertical USB connector that is on the PCB. And previously, the test module was, let's go for a side view. The test module was sliding in here, and the bottom of the module was striking the back of this USB cable. And I had that as a clearance problem. And my plan was to do two things. One is, in the short term, use a right angle USB cable to make that clear. And in the longer term, to move that USB connector further down, bring it down here somewhere so that it was clear. But I don't think I need to do that now. Oh, and the other thing is that there is normally a deck in here. You see these little slots on the sides, and there are notches on the back. This is all open because because I've basically just been experimenting, playing around with it, and I needed to be able to get to the Raspberry Pi easily. So I assembled this without the deck, but normally there would be a plate in here that protects all of the internals of the tester, and it just leaves you with an open cavity on the back where the test module can sit in. So now, if I drop the test module on, I'm going to turn it sideways so we can see through. Oh, there is now miles of clearance. Look at this. Look just down in there. That is where the USB cable sticks out. And if we look side on, the test module now slides in and engages with that edge connector. And there is miles of clearance below the bottom of the test module and the top of that socket, which is beautiful. That's what I want. So what I think I'll do, you can see where the notches are here. That is where the deck went through previously, and it fouled that USB cable. So what I'm going to do is change the design to move the deck up to be just below the module and just above the USB connector. So it's going to be in that gap right there. And that'll seal off which is also going to mean making the back higher. You can see the back plate here, which has got the power switch on it, power socket, there's some USB sockets there. This back plate is going to need to become higher because the deck will be just below the height of that test module. But for now, that doesn't matter. We can run it without that. So now, the test module sits in the chassis, slides in, push, and it engages. So the edge connector is now engaged. The module has slid forward, and it is up against the end stops. So there are end stops here on these side plates. And that, I am amazed to say that this actually fits beautifully. Fits so well. It's very hard to show on this, so I think I'm going to switch back to the front camera and wave it around up here. Because it's significantly larger than Testomatic 1.0. So there's a side view, you can see the touchscreen on the front, little rubber feet underneath it, test module on the top. It's all coming together very nicely. Power and everything on the back. Yeah, so I'm going to need to revise the back plate, the side panels to move the slots up for mounting the deck, and then mount the deck at a higher location. And I also want to put mounts on the side for a cooling fan. And also on the back, there is going to be a USB hub mounted in here. I've got some hubs on order. I ordered some little USB hubs from China, but they haven't arrived yet. And what I'm going to do is cut a slot in here and mount a USB hub in the back. At the moment, what I've got is this USB panel mount cable. So there are two USB sockets on the back here, which are panel mount, that cable goes through and plugs into 2 of the USB sockets on the Pi. So I'm using up 2 sockets on the Pi to bring 2 connections out the back. One of those connections will go to the label printer. One, temporarily it might go to a USB hub, because then I can plug in a keyboard and things. And I also want to bring Ethernet out. So I've got Ethernet in there. The Ethernet socket is on the Pi. I want to bring out an Ethernet cable that runs to the back panel and then have an RJ45 socket on the back. So you can just plug in Ethernet if you want to. This one is set up for Wi-Fi at the moment though. Yeah, so, thing of beauty. Anyway, I like it. Oh, cable management. If we come around this side, you'll see a couple of ugly things. You see here we've got the HDMI cable and the USB cable going to the touchscreen. That is because I need a right angle HDMI cable that will come off the touchscreen, and I've already got all of the clearances. Oh, my computer went to sleep. It locked itself. Come on, unlock. There we go. Yeah, so I've already got a slot. It's a bit hard to see, but the panel that is holding up the touchscreen has a slot in it right here. Like, I can stick my finger through it. That is where the cable is going to go, and it will then pass through. You can see it there. There's a well, that way. There's the slot for the cables, and there is a hole for accessing the menu buttons on the back of the touchscreen. You can reach through, and I put a hole in the bottom of the chassis so you can reach underneath to get to the touchscreen controls if you need to. And so there'll be a right angle HDMI cable and a right angle USB cable coming out of the screen and going directly backwards. Oh, that's a better angle. So they'll be coming out of the screen, and instead of coming out sideways like this, they will go directly backwards inside the enclosure. So all of this will disappear, and it will be a totally smooth side with no cable protruding. Yes. Yeah, I just glanced across and I saw there were some interesting comments. Austin says, did you forget to use a section analysis in Fusion when designing? Yeah, I never actually did an assembly in Fusion. I designed, what I actually did was I designed the PCB in isolation and then thought I'll figure out the mechanicals around it later. And that was probably a bad idea. Oh, Scott says that I need a HUD in my glasses for the chat. I definitely do. Okay, I'm scrolling way back in the chat. If the DuPont... oh, hasn't slept properly. Oh, okay, so Austin said, oh, Austin got a 2011 Ford Escape, needs some long-term wheels, and this one can tow a trailer for the trike. We'll end up working on it. Yeah, Austin has got a very interesting electric trike project, which is cool. Wagon Load said, if you need to connect test cables to the bottom of the test pins, can't you run all of the test pins to the back edge right angle connector? Back edge right. Yeah. Yeah. So I was trying to parse that. So Wagon Loads, I think what you may have missed is that all of those test pins are connected to traces on that test pin carrier PCB. So as Scott said, the pins do all run to the card edge connector. Scott said you could now raise the deck above that plug. Yes, exactly. Did you forget to use section analysis? At least don't forget to leave space for the rubber feet. Yep. Do you even need the deck? Yeah, that's a good point. So Jack's Tech said, do I even need the deck? It will almost always have a test module. Okay, so, whoops, wrong button. So the thing is, yeah, maybe I don't. So if I remove this test module and just put it aside, right now the tester is totally open and exposed, which is not necessarily bad, but you can see here that all of the cables, everything inside the tester is exposed. I did actually initially assemble this with the deck, and I quite liked it, because what happens is that with the deck in place, you end up with just a totally enclosed body and the cavity on the back here, and the only thing exposed is the edge connector sticking up above the deck, and then you can just slide the module in. So the top part of this PCB is exposed, but everything else is totally enclosed. And I quite like it from an aesthetic point of view. You can still see everything inside. Yeah, you're right, it doesn't really need it. Just a warning, I can feel a sneeze coming on. I am way better than I was previously, but I'm still not actually 100% healthy. Very close, but not 100%. So I may have to hit mute in a hurry. Where are we? Crispian says it looks like ORAC. ORAC, what am I missing? ORAC. From Hitchhiker's Guide. ORAC. Was it from Hitchhiker's Guide? ORAC. Yeah. I don't know. Anyway. Internal, Crispian said, internal flashing lights for more ORAC feel. Yeah, I was thinking about putting a connector on the Testomatic PCB for driving an addressable RGB LED strip, and then run the strip around the inside of the enclosure, because what I could do is make the whole enclosure go green for a pass or red for a fail. That is on the wish list for the future. In fact, let's Testomatic. Let's do this. We'll do this, and what have I got? Is there a to-do? Vim, to-do. Let's see. Connector for RGB LED strip to illuminate enclosure. Illuminate enclosure. Yes. So what have we got? Let's just check if there are things I've already done. Length match USB, increase thermal relief, blah, reverse, add solid working area beside, add bolt holes. Yeah, okay, so these are all still to do. None of these have actually been done yet. Okay. John, okay, so flat flex cable. Simon said use flat flex cable for those. I think that's referring to the cables that come off the touchscreen, perhaps? Yeah, if I could get flat flex cables, that would be cool. I just haven't found anything appropriate. I have, the funny thing is, I may actually get a delivery today, maybe even, oh, hang on. Oh, I got a notification earlier, and I didn't, hang on. I'm going to see if I can do, oh no, it's my other phone. I've got notifications of deliveries. Hang on. I'm going to switch you to this view. I'm going to keep talking to you. I'm going to go to the letterbox. This may be the most timely delivery notification. I don't know if you remember, but right when the stream was starting, oh, look at this. I've just come to my front door. right as the stream was starting, in the middle of all of the random chaos, I got notifications on my phone. I was distracted just as the stream was starting. They were fast horse delivery notifications. So now we get to do a live unboxing. How timely is this? Let's see what we've got. Let's see. What have we got here? What is this one? So I just looked at my front door, and these packages literally arrived as I was starting the stream. Ooh, there's a right angle HDMI adapter. Now, I don't know about the clearance on the edge of this. I ordered a couple of different types because I couldn't really tell from the ads which type I would need. Let's try this one. Yeah, this is as live as it gets. Oh, it's a package inside a package. This may be test pins, because I ordered different types of test pin carriers as well. Test pin holders. It is! It's more test pins. And what I have here is test pin holders that do not have the pins on the back. So these ones, so that is a test pin socket with no pin sticking out the back of it. So they're shorter. With the ones on here, these were originally test pin they were pin sockets with the pin on the back, and I cut them off to make them shorter. So these ones don't have the pins on them in the first place. So that's cool. So I've got an assortment of new types of test pins, different styles, and different types of carriers. What else have I got? What's in this one? Oh, rubber feet. Not the most exciting thing, but necessary. So I've been short of rubber feet to go on testers and things, so I ordered some feet. Okay. Well, I only got one of the types of, how many of these did I order? Maybe there are other types in the same. No, it looks like they're all the same. Yeah, I ordered several different types of right angle HDMI adapter. So, what am I going to do? I want to try. I want to see if this fits now. Now, what's the time? It's now 10:49, and we still haven't even got to hardware bring up on this yet. I'm still just ranting and raving about things. Now, okay, I'm not going to do it right now. I don't think. Oh, will it fit? I want to see if it'll fit. See, the problem is this adapter protrudes a little above the connector. You see, it's not, and the critical thing is this little bit, this nub sticking up the top of this right angle adapter could foul on the body of the display. So if it goes in there, I'm not sure if it's actually going to fit into that socket. It looks like it probably will. Can I get it in there without actually disassembling everything? No, not quite. Doesn't quite fit. I'll have to take this front panel off in order to try that. Yeah, do I? Don't I? Yes, I do. I do. I can't help myself. There it is. All right. I'm going to make myself some room on the bench. I've just got to take out 4 of these little M2 screws, and then that front panel will come off with the touchscreen. So it's not really too difficult to do. And I'm back to ignoring the chat again. Yes, I need a HUD. I need to be able to see the chat while, or to have someone here with me who is talking to the chat. Okay, so that is the laser cut mount for the touchscreen. And what I need to be able to do is get this right angle adapter in there, plugged into the touchscreen, so the cable comes out through this slot. Now, to make that happen, I've got to undo this. So, just take, I might not have needed to take it off entirely. I probably could have just loosened it. Okay, moment of truth. Does it fit? Just, it's very tight. The clearance on this, I'm kind of tempted to actually like grind off the top ½ millimeter or something just to make it clear a bit better. Or just, yeah. No, I think that works. I think it actually goes in. I think that's fully engaged. That's as far in as it goes. So now, does this fit? Oh, it does. Look at that. Look at the positioning. Hang on. Sorry. As I said, I'm not quite well yet. All right. This cunning plan is working out. It's coming together. So I'll screw that back on. So now we have the screen with a right angle adapter on the HDMI connector coming through the back of the panel. So what I need now is the same thing on the USB connector. I need a right angle USB cable that comes out through this slot, and then everything can be contained within the enclosure. And you can see here that I brought the cable out from the hole under the enclosure. Right, I'm going to bring this one back in, take that back in there, plug it in, and then try mounting it, and we'll see if HDMI works when we power it up. Okay, sit the mounting bracket back in its position. It's just a little bit tight on these tabs. I need to tune the clearances on the tabs slightly. Take 1/10 of a millimeter or something off them, just to make them sit into the slots more easily. There we go. Now, screw this front panel back in. Oh, while I'm thinking about it, next weekend is barbecue weekend again. The time has come around again. So if anyone is in Melbourne and wants to come along to hang out with me and a bunch of other random nerds next Sunday, come along. Okay, so you can see that ultimately that's what it's going to look like, with a nice clean side on it and no cable sticking out. And now the HDMI cable is internal to the enclosure. But just for now, I have to run this USB cable around the outside and plug it into that one. And that provides power to the display and also the connection for the touch interface, so that the Raspberry Pi can detect touches on the screen. Yeah, and we are now ready for power up. Turn on the lab supply. Got to grab myself a little power extension cable, one of my XT60 extensions, because everything here is XT60 except for the things that are XT30. Okay, power. Also, I'm pretty confident there won't be any smoke coming out of this. I have powered this up already, and so the power supply part of it works, I know that. The Raspberry Pi runs. The touchscreen has been working, although now that I've just changed to this adapter, we'll see whether that continues to work. What have I got? 12 volts, 2 amps. That'll do. So what is happening here is we've got power coming in from a lab power supply. It goes into this connector on the back panel. There's a power switch. I'll turn on the power supply. Power switch, power goes through to this XT60 connector here, which is on the Testomatic PCB. From there, it goes to 5 places. There's a 5-volt regulator here, which is switched through to the device under test. There is a 5-volt regulator that supplies the Raspberry Pi. There is a 3.3-volt regulator that is switched through to the device under test. There is a 3.3 volts that goes to the test circuit. And there is raw V-in, which is also switched through to the device under test. So it gives us a bunch of options. So this Raspberry Pi has an SD card in it running Raspbian, and I have previously booted it up, had it running, got it on the network, etc. So if I turn on this power switch now, we've now got the red LED. You can see we've got 3 power LEDs. Oops. We've got 3.3 volts is blue, 5 volts is red, V in is green. So we've got the 3 power rails here, which are the power rails for the tester itself. Then we've got the 3 power rails over here, which are currently all turned off because the relays have not been activated by the Pi. So these power rails are for the device under test. These power rails are for the tester, and they are separated. And the device under test power rails do not turn on until the Raspberry Pi tells them to turn on. Oh, look at that, we've got the screen up, and touchscreen is working. Hang on, I'm going to rotate this around here. So, well, that right angle HDMI is a total success. That's really cool. So now I've got the touchscreen. That's a, what is it, 1024 by 600, I think, is the resolution on the touchscreen. And I could select menus from here, internet, but I'm not actually going to open anything. We're going to SSH into this and mess around with it, because the thing I really want to do today, in fact, I'm going to, where's that thing? I dropped a, there we go. I dropped a hex thingamajigamy. Where's the test module? Oh, it's right here. I probably shouldn't be hot plugging this, but I'm going to grab this test module and slide it into place. Ooh, cool. You can see the LEDs lit up on here. There is a blue LED and a red LED showing 3.3 volt and 5 volts going to the tester. And there are also 3 LEDs there that are not illuminated, which are basically matching these ones. So they are showing the 3 power rails that go to the device under test. So Testomatic is now fully powered up. It has a test module in place. Power rails are up. Touchscreen is working. Yeah. I'm kind of slightly baffled that this project is all coming together. Oh yeah, and these things, I've got to tell you about these later, if we get to that. Let's see if we get through this other stuff first. Oh, but before that, I'm going to try to catch up on chat. Oh yeah, there was a mention, okay, a couple of mentions. Scott says, Smart Hub, yes, that is in my plans. I'm going to get something open here. Testomatic. I'm going to show you what I've got so far. And it's a partial implementation of the way that Austin has been doing it. I'll get this up on screen in just a jiffy. Here we go. Okay, so this is the Testomatic PCB, the 2.0 version, which is what's currently in it. I also have a 2.1 version where I have already moved this vertical USB hub, this vertical USB socket, all the way down here, down into this sort of area to clear the deck, but I may not even need to do that now. So we've got the power rails for the device under test, and in the schematic, where's the hub? Hub? No, not there. Here. Okay. So this is the USB hub, which is on board the Testomatic PCB. We've got that connector here. This is that vertical USB-C connector, which is the one that goes to the Raspberry Pi. So the Raspberry Pi connects in on this port, this USB port, the one labeled upstream. It comes to the TUSB 2046 USB hub chip, and then there are 4 downstream ports. So DP, DM1 for data positive and minus for port 1. So we've got device under test USB ports 1, 2, 3, and 4 with their associated noise suppression sort of stuff and filtering circuitry. So what I'm missing here is all of the smart stuff that Austin has done on his smart hub to do power control and isolation and things for each of these ports. So what we could be doing is turning these ports on and off on demand, which could be an incredibly useful thing. So in a future revision, I think what I'm going to do is totally copy from Austin's clever design and incorporate some of his control into here. And it might be useful, I'm not sure it'd be useful for doing current sensing, because the actual purpose of these ports, it comes into these little modules, which I mentioned a second ago. What the actual purpose of these ports is, it's not likely that this would connect directly to the device under test. What this port is going to go to is some extra peripheral that is specific to the test module. That might be a USB to serial converter. It could be an RS485 interface. It could be, I don't know, whatever else you want to stick on USB. So the device that this connects to is probably going to be part of the test module, not connected through to the device under test, although it could be, in which case things like current monitoring, etc., could be a useful thing. So this all goes onto the, hang on, let's come back to here. Blatantly steal Austin's smart hub design. Okay, that is on my to-do list now. Yeah, so I can incorporate Austin's work into this. So, what is there? All right, so we don't even know if this hub works yet. I haven't validated any of this. Apart from the fact that power works, that's all I know. Now, where are we? Okay, so we've got the Raspberry Pi header. We've got power LEDs, we know they work. Don't know if the HAT EEPROM works, don't know if the piezo works, don't know if this works. What else have we got? Oh yeah, those are the voltage regulators. We don't know if the I/O expanders work. We don't know if the ADCs work. We don't know if the DAC works. this is all to be tested, and we don't know if the USB hub works. It's an adventure. Now, where are we? Okay, I am so far behind. I'm like 30 minutes behind in the chat now. Okay, so John Whips asked, didn't go for a ZIF connector. No, because I think a ZIF connector would be ideal, but I had trouble finding one that wasn't a ridiculous price. I went looking for ZIF connectors and they were like $100, $150 for a PCI ZIF connector. And there's a big difference between that and $3 for a regular PCI connector. So yeah, I didn't want to just go out buying $150 connectors. It'd be as much as the rest of the parts in the thing. Sharky says, morning all, just back from 6 weeks in Europe now, the weather is warming up. Nice. Yeah, the weather is starting to get better here as well. Oh, excuse me. Now, there was a discussion about PoE. So Stephen suggested PoE plus 60 watt. Potentially the tester could be powered off PoE. Austin disagrees strenuously and says PoE here is a terrible idea. If something malfunctions and you get to replace an expensive switch with it. Yes, that's true. Although ideally there would be enough isolation because of the voltage regulation that is within it. At the moment I've got raw V in being passed through to the device under load, the device under test, but that could also be done in an isolated way. So it would be possible to protect upstream and power the tester off PoE, but maybe that's a future thing, possibly. I think it would be way down the feature list though. I'm quite happy powering this off some external power supply. I've just got a lab power supply plugged into it. They're not especially expensive. You know, to Dremel the display. Oh, okay. Oh, DIY is here. DIY asked, hey John, how are you? The answer is, as you can hear, still a little bit coffee, but generally good. To take you up burst. Okay. Unexpected item in the delivery bagging area. Right angle ads are never clear enough. Yeah. A dozen useless right angle USB cables because the ads are never clear enough. Exactly. I ended up ordering several different right angle adapters because they, and also with HDMI, of course, it's directional. You need one that is going to bend in the correct direction. And so I ordered, and you can get some that bend with the narrow part to the top, some that bend with the narrow part to the bottom. And the yeah, anyway, I ordered a couple. The thing is, these adapters, like these little right angle adapters, they're only like $3 each or something. So I ordered, how many was in this order? 5? 6? Something like that. So I ordered like 5 of each from several different vendors in the hope that one of them would be suitable. And this first one that arrived, turns out it is suitable, which is unexpected and good. Scrolling, trying to catch up on the... Scott says felled sockets are worse than felled nubs. No, John asked text to speech. No, text to speech is not running today. There is a server upgrade happening on that right now. In maintenance mode, people talking about Dremels. This is way back when I was plugging in the HDMI. Did you get a right angle USB? Stephen asked. I've ordered it, but it has not arrived yet. The question is, when you buy it from the first, dangly cables be gone. Do you have an XT60 battery pack? Asked Wagon Loads. Yes, I do. I have standardized on XT60 for most of my power related needs. So I have batteries with a few batteries with XT60 connectors on them, and I've got XT30 batteries. I've got XT30 to 60 adapters, XT60 to 30 adapters, and like male to female and female to male and all the different combinations. If you need any XT60 stuff, I have got it. It's I've got a laser cut sitting up to my right is a laser cut cable hanging thing with a row of cables in it with XT60 connectors, and they go to 2.1mm DC jack, to USB-C, to alligator clips, to like basically everything, all off XT60. So I can plug anything into my lab power supplies. Michael says at 10:59, John says, the thing I want to do today is... Don S says, awesome progress. Thanks, Don. Wagon Loads asked, does the test module have a ROM to tell the Pi which one it is? Yes. Austin answered that. Yes, it has an I2C chip with a unique identifier. And the tester itself has one too. Yes, so I will clarify that slightly, because this is something that I ended up doing. If we have a look in Sheets, the tester, and they're on two different I2C buses with the same I2C address. I think it's hex 40. That's something we're about to discover. So what you can see here is the IO0 and IO1 EEPROM, SDA, and SCL coming off this I2C EEPROM. This is the EEPROM that is specified as like in the reference design for the Raspberry Pi hat specification. And this particular I2C bus is only enabled during the boot process, and then it's disabled automatically by Raspberry Pi OS. And what it does is it brings up that bus on startup, it probes for an EEPROM, and if it finds it, it loads the contents. You have to put some stuff in there in a specific format, which is documented, and that tells the Raspberry Pi what drivers and things it needs to load to support the hardware that you've got plugged in. So this particular EEPROM is essentially, if you think of the Testomatic board as a Raspberry Pi hat, which effectively it is, then this is the EEPROM that identifies the Testomatic. So the Raspberry Pi knows that a Testomatic is plugged in. That is the theory. And then there is a second one of these EEPROMs on a different I2C bus. So if we come up here, this is the edge connector that goes up to the test module. So we've got all of the power rails there on that first section. Then there is the key, and then we've got, so there's a 5V and 3V3 here. These are the tester power rails. These are not to go to the device under test, because there's 5V here to go to the device under test. That's switched and monitored with a current sensor. This is 5V for the use of the test module for its own onboard stuff. Likewise, the 3V3. And you can see here, we've got IO2 and 3 as SDA and SCL, as opposed to down here, wherever it was, there, IO0 and IO1 as SDA and SCL. So we've got two I2C buses. This one, it goes to, this is not intended to pass through to the device under test. This is an I2C bus for use of the test module, and that includes the EEPROM on the module. So there is a second EEPROM There is this one on the Testomatic. There is a second EEPROM on the module. So when the module is plugged in, we can use I2C to probe it and find what module has been loaded, and then select the appropriate tests to execute and have it come up on the display showing what device it is that we're going to be testing. At the moment it's all done using a menu on the touchscreen, but I want to change it so that it identifies it based on the ID stored in the EEPROM. Tassie Bob, good morning. Good morning, Tassie Bob. Where are we? Where are we? So the stage we're at now, hang on, the stage I'm at is trying to catch up on chat, and then we're going to start probing around with I2C. All right, tester itself has 1, 2. Austin says, yep, power and data control plus current sensing for things misbehaving along with protection against spikes. Yes, Don S says PWM for cooling fan. I do not have that on here. What I did was I've bought some cooling fans with temperature control modules. I won't bother getting those out right now. So what I figured was, what I will do is mount a cooling fan in the side of the enclosure for the Testomatic chassis with a little control PCB in it with a temperature sensor, and just run it off 12 volts. So I'm just going to run 12 volts from the main wiring loom to the fan, and it can be standalone. The Raspberry Pi doesn't need to care about it. And the Testomatic PCB doesn't need to care about it. It'll just be there in the enclosure doing its thing. Where are we? Stephen says, I don't think PoE is required, just saying it would need a lot of power. Yeah. Sorry, scrolling back up in the chat. Austin says, no use EMC 2101 for the fan. I don't know what an EMC 2101 is. Is that like a standalone fan control thing? Oops. Where are we? Integrated fan control solution. Yes. Yeah. I ended up just ordering, hang on, I'm going to find the, you get to see my order spreadsheet. My Superhouse automation parts ordered. So where are we? We've got, oh yeah, these are the 4-port USB hubs. I ordered a 5-pack of hubs, $7 each, for the to go in the back of it. Oh, some solder. Oh look, I ordered another 10 feeders. Feet. Yeah, these are what just arrived. These just arrived. These just arrived. Hang on, why are there 2 types? Oh, okay. There must be 2 types in that bag. All right. Oh well. So what I can do, in fact, what I'll do is mark those off. So these just arrived, and they arrived, when was it? 1st of September. So 9 days. They just arrived. Oh, don't mind me, I'm just doing some housekeeping. And that just arrived. 1st of September and 1st of September. Okay. What am I doing? Fan, here we go. 5cm cooling fan with temperature and speed control. They were $11.61 each. And this is what I ordered. So it's just a cooling fan with a little control PCB. Don't allow. So it's a cooling fan, control PCB, and power input, and a temperature sensor. That's it. So all I've got to do is mount this in the enclosure, and these have already arrived. I've got them. I just haven't physically mounted them in the chassis yet. So this will just sit there in the chassis, with its temperature sensor and turn it on when necessary. Yes. Yeah, these. I'm waiting for these to arrive because I want to be able to mount this USB hub in the back. Okay, back to the chat. I am trying to catch up with the chat. Crispian asked, can you rig up a fault tester test by switching faults on and off on a testable board? Ooh, yeah, well, you've got to test the tester. Yeah, that is a bit of testception. Test inception. I have done part of a design, I haven't actually finished it yet, for a Testomatic test module. It is this one. I need to do a fair bit of refinement of this design and rethink a few things, because what I want to do is have a starting point for people building their own test modules, and this is it at the moment. So I've got the edge connector broken out to different nets, and then I've got LEDs connected to GPIOs, so I can drive GPIOs and do like little scanning patterns and things on it. I've got loop backs between DAC channels, so I can generate signals on the digital to analog converter, and then I can read it back in on the analog to digital converters. So it's got loop back on those channels. It's got display of the status. There's the ID for the EEPROM, the ID EEPROM that identifies the module, and that's it. I think it's only that one sheet. So this is where are we? Oop, no, not that one. I wanted T-place. Yeah. So it's just a short board with a bunch of LEDs on it. It's got the power and things, and this is the loop back on the analog down here on the right. So you could plug this into the Testomatic and then use the Testomatic to send signals out and measure them back in and drive the LEDs to verify that the I/O works, etc. I don't think that's quite what you were talking about, Crispian. I think you were talking about deliberately inducing faults so that you can validate that the tester picks them up. That is, yeah, seeing a test fault is a very useful thing. Where are we? Peter says my brain hurts. Yes, my brain hurts too. Scott says, careful when you go to test the piezo. I had 2 cats try to claw their way out of the house while testing a device with a piezo yesterday. Oh, those poor kitty cats. Stop banging the desk. Scott said, there was this conversation about, so Peter said, my brain hurts. Scott says, so stop head banging the desk. Peter said, where's the fun in that? And then Scott said, back when I still worked in R&D, I had a designated spot on my desk, even had a bang head here sign on it. Austin says, see the link. All right, let's see. I'm going to click on the link. Ooh, that is interesting. All right, that is very interesting. Thank you to Simon, I think it was, who originally posted that link. Yeah, cross-posted from Simon on Discord. Oh, this is very interesting. Yeah, adapters, like different breakouts with ribbon connections. That could make all of the cable routing very neat. FFC, how long is it? Does it come in different lengths? 5, 10, 15. Oh, it does too. Oh, yes. Connector A1. So some combination of these could make a really cool, neat little route for it. So what I would need is HDMI on one end, micro HDMI on the other. Mini HDMI, do they do yes, they do micro HDMI as well. This is perfect. So neat. Yeah, Simon says they're awesome as you can make any cable you want. Yeah, you could do a combination. So on one end, have right angle HDMI. I would need A2. So it's the right angle going in that direction with the narrower side on the outer edge. A3 is the other way around. And then the cable in the middle, and then micro HDMI on the other end. I don't know which one of these. I'd have to work out which way the cable is going to come through. Yeah. So you can mix and match to make a connection from anything, like any angle, any size, to HDMI to any angle, any size on the other end, and then use the appropriate length flex cable. Simon, thank you for pointing that one out to me. That is really nice. I think I'm going to take some measurements and figure out how I would make all of that fit, and maybe order the appropriate parts for that. Yeah. Oh, they also have USB, and they all use the same 20-pin flat flex. Oh, nice. Very nice. Scott says, would be cool to find the same package for USB. Yeah, well, Simon says they also have USB. So from that same seller, perhaps, if you have a working, if you have a link to it, that would be really handy. And all the angles. Yeah. Whew. Scott says, yes, need a link for the USB version. Needs it, precious. Yeah, they look cool. I think that's the find of the stream so far. Simon says, I'll post the link on Discord, same seller. Excellent. I will check Discord. So Scott, check Discord later, and hopefully Simon will have that link in there. Now, what are we doing? We are going to here and going SH Testomatic at tester 3. Okay. Hopefully it is up and on the network. Looks like it might be. Testomatic is both the username and the password. Super secure. And I've just doxed the credentials to my tester. But this is obviously a dev thing at the moment. Now, what have we got here? We've got all of the default Raspbian stuff. Sudo raspi config. I think there are a couple of things I need to do. I need to enable SPI. Yes. Cool. I want to enable I2C. Yes. And what else do I need to do? Let's just check if there are any updates. Are there any updates to raspi config? This should, basically what you're looking at here is a default installation of the latest 64-bit Raspberry Pi OS, and then 75 not upgraded. Okay, it was configured to connect to my Wi-Fi and SSH turned on, and that's pretty much it. So what we need to be able to do is see whether we can detect the I2C devices. So we'll finish that. So let's see if there are any package updates. Oh, haha, nice. While that is happening, oh, it's a thing of beauty. Like, here are all the different USB thingamajiggamies. Let's see how much the connectors are. Yeah, it's not particularly cheap, but it is very neat. Like, look at this. So what you would need is something like a connector on one end is $6. Then you've got the cable. So say 20 centimeter, that's $6 for the flat fiber. And then you might need a connector on the other end, which is another $6 So you're talking about like $18 to make one cable. It's not cheap, but it does allow you to deal with situations that would otherwise be very, very difficult. You can build anything to anything, and you got all these different angles, like the different, the different orientations of all the different connectors. So if you're in a sticky situation where you need a cable coming out at a strange angle from something and you've got very little clearance, this is a really good way of solving that problem. Anyway, the links are in the chat if you're interested in that sort of thing. Back to here. Sudo apt dist upgrade. I'm kind of inclined to not let this go through. What's it going to upgrade? A whole bunch of stuff. All right, I'm just going to let it get started while I am thinking about the next thing, because what I'm going to need now is I'm going to have to go into my unhappy place and Raspberry Pi Python scan I2C. Let's see how we do this. How to scan and detect I2C addresses. Oh, it's already it's already got I2C detect installed. All right, so we need to do that, and then we can do, oh yeah, and then we can say what bus we want to scan. Nice. Okay, that'll be super easy. So I'll just let this do its package update, and then we will scan the bus. And while we're looking at that, well, while that's happening, what addresses are we expecting? One of the things that I try to do with most of my projects is document I2C addresses, and I was either lazy or dumb, and I didn't do it when I was putting this one together. Oh, hang on. There we go. I partly did. Okay, so hex 48 and hex 49 are the two ADCs. Hex 60 is the DAC, and then I haven't documented it on these, but they're just the MCP 2307Es, which are, that'll be 40, I think, by default. Ooh, I just had a horrible thought. I wonder if that address, yeah, this one, so this is all address pins pulled low. That is going to be hex 40, I think. MCP 23017 I2C address. Oh no, 20, that's good. Because the reason is that I think the EEPROM is at 40. So, 20, 21, all right. This is, I'm going to do some documentationalizing just here. And let's stick it up here. And move this over here. I2C addresses. 0x20 will be MCP 23017, IO 0 to 15, and then 0x21, MCP 23017, IO 16 to 23. Then we've got, I think it's, I'm going to have to check this, but I think hex 40 is going to be the tester module EEPROM. Then we've got, oh, I can't remember what they were. Was it 458? I'm going to put some bogus values down here for now and then change them because my memory is not that good. That was ADC 0 to 4. And then 59 was ADC, no, that's 4 to 7. That was 0 to 4 to 7, 0 to 3, and then another bogus address because I can't remember what it is. let's say 70 was DAC 0 to channel 0 to 3. So that'll do for now. Let's see what those addresses actually are. Here. So we've got, oh yeah, 48, 49, and 60. Okay. That wasn't that far off. Just off by by a digit, by an order of 16. So that was 48, 49, and then that was 60. I think that's it. All right, now has our dist upgrade finished? It has. So I'm going to reboot. Oh no, I'm not. First, I'm going to do this thing, and then I'm going to reboot. It's already installed. Sudo reboot. Gotta make it bigger, easier to read. Come on, bigger, bigger. There we go. Okay. Yeah, Austin says, not cheap, but it'd make things so neat. Yeah, this is in relation to the modular USB cables. Now, one thing I'm curious to know, a bit of feedback from people. Is anybody interested in this, apart from like just following along at my journey and laughing at me, at my, it's rebooted, yep, at my incompetence. If there are people who are interested in this as an actual thing that you want, please let me know, because I'm building this primarily for my own purposes. This is something that I want and I need this device, so I'm building the Testomatic. But if other people want this for their own purposes, if there is a market for this in particular, like if people want to just like buy them from me, pre-assembled, ready to go, that would be really cool. So, Scott says, don't forget to sync the repo at the end of the stream. Yep. Now, back to here. I2C detect first bus. All right, here is moment of truth for I2C. What have we got? Look at all of this success. Look at it. Oh, and it's finding things that I hadn't thought about, but are absolute, yeah. Okay, I forgot to include this. This is the current sensors. Oh, this is cool. Okay, I'm going to do this and do that again, just to put it up near the top of the screen. Can I resize this window? Here we go. Okay, so what we have found are the first two MCP 2307Es, because there are only two so far. I think I'm going to have to add another one. How many am I doing? Yeah, I think I need to add a third, because I've got 24 pin GPIOs defined on the edge connector, but I'm only using the first 16 at the moment. So this version of the PCB it's kind of validating the basic functionality and the concept, and then I'll add more channels. So what we've got is the first two I/O expanders. That gives us a total, what am I doing? 16. There are 16 per, anyway. Okay, two I/O expanders, that's the point. We've got two I/O expanders, then we have 4 INA 260s. These are the current sensors that are used for the 3 supply lines going to the device under test. So we can measure the current that is being pulled by the device under test on each of its power rails. Then we've got 48 and 49. These are the analog to digital converters. They're 16-bit ADS 1115, I think from memory is the part number. So we've got the two analog to digital converters. They've come up on the bus. And then this one, 60, that is a 4-channel digital to analog converter. So with that we can generate analog signals within the 0 to 5 volt range. I can't remember the resolution on that, but it's pretty decent. Might be like a 12 volt DAC or something. Could be higher. Always add things in binary increments. So add 2. Oh, Wagon Load says, I made a 3-pin jumper footprint for I2C address selector, so I can change it later if needed. Cool. Anyway, this is like success to the extent that we know the devices are on the bus, and it found the devices that I even forgot about. So 40 through 41. That is, if we come back to here, so we got, oh, hang on, maybe we have a problem here. Tester EEPROM, let's, because, okay, all right, I want to figure this out. I want to resolve this. So we've got 3 INA 260s here. This first one has both its address pins pulled low. Yeah, address 40, 41, 42. But what is the address on the EEPROM? I have a horrible feeling it's the same. Ooh, this could be annoying. I can feel a hardware revision coming on. Okay, so this is a Cat C. Yeah, all the address pins are pulled low on that. So, let's see. I'm just going to look up the datasheet for it. Cat 24C32 I2C address. What is its default address? I don't know why the theme, that theme came to mind. I2C address. Yep. Now, come on, give us the address. Yes, okay. Is this going to be one of those things where they don't actually tell you the addresses? They give you first 4 bits are set to that, must match the logic state of the similarly named input pins. Yeah, they don't make it easy, do they? Slave address bits. Okay, address bits, it's got the timing on it. Device address. So we've got control of those, we don't have control of those. And they're going to make us calculate it, aren't they? Screw that. I could do that. 50. Okay. Features a default I2C address is 50. Maybe. Hang on. We didn't get a 50. I wonder if that EEPROM is working. The one that is on... So that is the EEPROM that is on the test... Ooh, thinking this through. These are the ADCs, and I want to add more ADCs. So I may need to either add a multiplexer or change the address of the EEPROM. But in any case, it looks like the EEPROM is not working. I'm going to have to figure that out, probe that. Okay, let's try... let's try... What will we try? Can we talk to the MCB 2307s? No, I want to I want to check if the USB hub is working. So how do I do that? LS USB. Oops. Biolabs Inc. Hub. Is that it? What have I got plugged in right now? Linux Foundation. What device does that? Where are we? Hub. Yeah, so this TUSB 2046. What device does that identify itself as on the bus? I could just unplug it and see what goes away. No, but no, I can't. Can I unplug it? If I unplug it, I'll also lose. What will I lose? Nothing. I think it only goes to the hub, so I can unplug it and see what goes away. But anyway, TUSB 2046 device ID. Here we go. So it should come up as a TI class. So it should be device 0451 2046. And we do not have any device coming up as that at the moment. So it is quite possible that the USB hub is not working. Jackstack says, short the CS line. The CS line? There's no CS line to the hub. Unless you're talking about, is there a select line on the thing here? What do we need? EE clock. It's possible that my clock circuit isn't working, or there could be a whole lot of reasons. So what we should have is a 48 megahertz clock, I believe, going to here. So I could check if this oscillator is running. I could put a scope on that and see if we're getting a 48 megahertz clock going into it. What else do we need? Suspend is pulled to ground, mode is pulled to ground, bus power is low, and EE data is pulled low. Since Austin is the expert on these, yeah, sorry, Jackstech, yeah. No, what I'm trying to do now is just determine whether the USB hub works. Sadly, Wagon Load. So Wagon Load says, can you plug something into the USB hub and see if it shows up? Sadly, I can't. That is not actually an easy thing, because what's happening with this USB hub is these are the ports. So we've got USB 1, 2, 3, where is it? 1, 2, 3, 4. Where they go is to the edge connector here. We've got USB 1, 2, 3, 4 brought up on the edge connector to the test module. And those are available for the test module to use, but there's nothing actually connected to those pins on the other side at the moment. Now, that could be solved by connecting one of these little modules. All right, so I think it's time. What is the time? 11:50. I think it's time to show you this. How am I going to do this? I think microscope is possibly my best option. And zooming way out. What's the minimum zoom I can get on the microscope? Bring it. I'm going to have to adjust its focus here. Here we go. Okay, so this, many of you will have seen my ESP flasher modules, which have got a USB-C. In fact, I've got, oh, look at this. Here is one I prepared earlier. This is an ESP flasher module. It's got a USB-C connector there. There's a CP2102N there. Comes to a cable in this particular case. So there is this cable IDC cable that then goes to a plug that you put into the target device. So this little device is for reprogramming ESP32s off a USB-C connection. And this sort of thing will need to be, because I use ESP32s quite a bit, and I use both the new ESP32s with built-in USB and also old ones that don't have built-in USB. So this sort of thing I'm going to need to incorporate into my tester modules. And I thought what I would do is design a series of little modules like this. And what this does is it just connects, so it's a serial module. It's got these pins here. This is 5 volts in. I need a pointery device. So I've got 5 volts, USB data D plus, D minus, and ground. So this is a USB connection just brought out to a 0.1 inch pitch header on this end. There's a CP2102N USB to serial converter here. There's a 3.3 volt regulator. And on the output side, this is an ESP flash format header, but it's actually just a serial port with extra stuff for GPIO 0 control. So what that means is that you could drop this module onto your test breakout, like your tester module, and you now have USB to serial or USB to ESP programmer. And it just saves you implementing it. My goal here is to make it as easy as possible to design the test module. And the idea is that this test pin carrier PCB should be a matter of take the reference design, which includes the edge connector and the power and the EEPROM, expand it to whatever size you want, put your footprint there for your device under test with all of the test pin locations, and you're pretty much done. And then if you need something like USB to serial, you would have, let's switch to this. That was not very practical. In fact, let's switch to this camera. No, this. How many tries is it going to take? All right, so what you would do is on your tester, you would basically plonk down one of these modules, and you don't have to implement all of this circuitry on your test breakout. This little module takes care of it. And I've got another module like this, which I have already designed, but I haven't fabricated yet, which is an SPI to CAN bus module. Because it's a CAN controller with a CAN transceiver on it, because I need to bring CAN bus through to many of my test devices, and I want to be able to talk CAN bus from the Raspberry Pi. And now you can see on here, see those those pins there, those holes there? That is actually for mounting one of these on the bottom. And if I turn it over, you can see the pin headers just there. That is to mount this like that on the bottom of this, but I haven't done that yet. So what that will do is take USB from the hub in the Testomatic, convert it to a serial interface, and take it to the programming pins, because some of these test pins are the programming, I can't remember which ones. There's reset, there's GPIO 0, there's TX and RX for the ESP32, and they go through to the device under test. So by putting this module on the test pin carrier PCB and plugging it in, we'll get USB to serial coming through, and we can program the test board. Yeah, so my goal is to come up with a range of little modules like this that can be plonked onto test modules, to test breakouts, to solve most problems, just to make it easy, so you don't have to reinvent. Once again, it's about not reinventing the wheel. If I've already done the work of designing this little module, then you just design your test breakout, you plonk the module onto it, and hey, away you go. Yes, so what I need to do is attach that to this, plug it in and see if it appears as a USB device on the Testomatic. But I am a little... hang on, yes. I do need a HUD. Hang on, I'm going to come back and look at the chat. Aaron said, if you insert the daughter board, which also has an EEPROM, does that I2C address appear? No, the test module was inserted at the time that I did that. So, TI USB hub to 2046. Okay, are there USB pins on the test module you can bodge into? Oh, Austin says, I forgot the clock on the USB hub. Ah, what? Where? What clock did I forget? Where? Hang on. Got to get back there. Where is this? Where is the clock I forgot? I knew I would. I had to screw up somewhere. Otherwise, I wouldn't need to revise the PCB. And where's the fun in that? Okay, clock. Let's see the clock. What have I... Where's my screw up? What did I forget? Where? So I've got EE clock here, crystal pins 30 and 29. Where? There. Okay. Yep, I've got those marked as do not connect because I'm running an active 48 megahertz clock here driving into EE clock, which is the external clock signal. EE data. Yeah, okay. Cool. Jax Tech said, you didn't screw up, you created a teachable moment. All right, so Austin says, I've never used the external clock. Yes, I'm pretty sure this is the way I did it. Okay, let's have a look. I want to see for reference. Now, this is not quite the same, but you can see on here, this is the TUSB 2046. This is the first time I've ever used this chip. I've never used it before. But this is the chip that Austin uses in his Smart Hub project. Oh, which is cool. Austin, if you feel like it, drop a link in to your Smart Hub project. So yes, shout out to Austin's Smart Hub project, which has given me a lot of inspiration. So he uses the TUSB 2046. This is a 4-port USB hub. So we've got the upstream port, so 1 incoming port, and then 4 downstream ports. What I have used in the past is the TUSB 2036, which is the 3-port version of this hub. And that is what is on the rack 30, no, not the rack 32, on the OpenKO board. So let's just have a look at how, and I know it works on OpenKO, so let's have a look at this. Not quite the same thing because it's a 2046 versus the 2036. But I want to see what I did on the OpenKO and in what ways I may have screwed this up. Wagon Load says, I did not fail. I just found 10,000 ways it doesn't work. Oh, cool. Austin has dropped in the link to his repo. Smart USB Hub. This is Austin's Smart USB Hub. For anybody that's interested in that sort of thing, I highly recommend looking at this design. So what Austin has done is put in INA 219 current sensors, and he's got power control and isolation and all sorts of stuff. Are there any photos in here? I don't know. Design 1, Design 2, Smart Hub top, PNG. There we go. So it's a Smart Hub with an ESP on it so that it can do all sorts of clever things and control the devices that get plugged into it. It's a hacker's hub, more than just plug it in and have 4 extra ports appear. All right, so what oh, hang on, I shouldn't have closed that. What I should have done, I'm going to reopen that and then I'm going to come back to here. Okay, so this is the TUSB 2036 on the ooh, there we go. Maybe that's my problem. Oh, why did I connect it to there? EE clock. So what I did on the, so this, as you can see, is the TUSB 2036. I think I need a bodge wire. I think with a bodge wire, this should work. So I've got the TUSB 2036. I did not have, what did I have? External mem pulled high. I had EE data pulled high. EE clock left floating. Why have I done this so radically differently? I have no explanation. My stupidity knows no bounds. So what I've got here is the 48 megahertz clock, and if we come back to Testomatic, you can see that same 48 megahertz clock. It's the same part. So this clock on Testomatic is the same as this clock on Rack 32, which I know works. And here, I took it into Crystal 1 clock 48 input. Yeah, clock 48 makes sense. That's 48 megahertz clock. And here, Crystal 1. So if I change that from EE clock into the Crystal 48 pin, maybe it would work. All right, let's go back to here and go for TUSB 2046 data sheet, because I want to see if Crystal 1, like Xtor 1 pin, is where I can XTAL 1 6 megahertz. Why is it 6 megahertz? Okay, so here it says an internal PLL then generates the 48 megahertz clock. Can use a 6 megahertz crystal input. Ah, I think I was just stupidly assuming that the TUSB 2036 and 46 work the same way. TUSB 2036 data sheet. Let's see. XTAL1. Here we go. Yeah, mode select. Ah, okay. So mode. When mode is low, it's selected as the clock source to drive the internal core. When mode is high, the clock on Xtor 148 is selected and a 48 megahertz oscillator is used. So this is what I've done on OpenKO. So I've got mode, was it mode? Yeah, when mode is high. And on OpenKO, I've got mode pulled high, which means apply a 48 megahertz clock on Xtor 1, as it says right here. But the TUSB 2046 is different. It says, yeah, so it generates the 48 megahertz clock itself. So it must upsample. So it says it allows either a 6 megahertz or a 48 megahertz clock. Test mode is high, clock input. Oh, okay. When TST mode is high, the TST PLL 48 megahertz clock input is selected as the input clock circuit. Okay, that is what I want. All right, so I need to pull test mode high, and then I need to send that 48 megahertz clock into the test PLL input. So here we go. I want, no, wrong one. This. I want test PLL pulled high. What's with the rendering bug in here? All right, so look at this weird rendering bug in in Fusion. Oh, that's a new one. I haven't seen that before. I'm going to switch to a different window, go back. There we go. It's re-rendered. All right, so test PLL is pulled high. Okay, that's good. But what I need to do is send the 48 megahertz clock into, so what pin do I send it into? The test PLL input is selected as the clock input source. Test PLL is, no, I'm misreading this. When test mode is high, where's test mode? So I need that to be the, mode. Maybe it's just the mode pin. Is that pin 31? Mode. The labels I've got on my signals here are not the same. Pin 31. What is pin 31? Is test mode. Yeah. When I was doing this footprint, I should have put TST mode. Okay, so this is what I've got to do. I have got to cut the mode pin and pull that high. Okay, then I need to cut the test PLL pin and link that to the clock output. Okay, so in fact what I'm going to do is, here we go. I'm going to come back over to Testomatic. What am I doing? Superhouse projects, that's what I want. There, Testomatic. No, not there. Testomatic and Testomatic 2.1. So this is one where I've already started making some changes. Okay, I'm going to apply these changes to 2.1 and then I'm going to patch the changes onto my 2.0 board. Well, at least this justifies a 2.0. I mean a 2.1. All right, what have I missed in the chat? Pin 31 is TST mode. Yep. Cable tie, you made it. Yes, and happy Father's Day, Cable tie. Yeah, Scott says you're good at showing up for the start of overtime. Yeah, we're into overtime rounds now. This is this is when come on, where's the hub? Okay, let's do this, people. Let's fix this. So what I need to do is I do not send the clock into EE clock. I send it into test PLL. Okay, so that's the first thing. I need to take this and link that into test PLL. I'm saying test, but TST I don't think is actually test. So TST PLL. Then I need to isolate mode from ground, and I need instead to pull it up to 3.3 volts. And I think that's it. I think that will fix the design. Oh, Cable Tie! Congratulations on becoming a grandfather. Grant is here too. Welcome, Grant. So, Cable Tie, your first Father's Day as both a father and a grandfather. Congratulations. All right, so am I now interpreting this correctly? Mode I have now pulled high. It's now pulled to 3.3 volts. EE clock is now not connected to anything. And I'm just going to put a do not connect marker on EE clock, and test PLL is now getting the output from the 48 megahertz oscillator. I think that'll fix my problem. I think it will. So what has that done on the PCB? All right, it'll have made some changes around here. So this is the version 2.1 PCB that you can see I've already moved the USB connector down here, nice and low. I might not actually even need it that low. It might get in the way. I moved it down there to clear the deck and the test module, as you saw earlier. Now, the other thing is that these buttons here, these connectors for the infrared camera and the external button, I think they may need to move all the way down here as well, because the deck comes across somewhere. See where my cursor line is? It's somewhere around here. It's part way down the relays. So what I need to do is get everything below this height. So maybe what I can do is if I take these connectors and I put them down here somewhere, that'll bring them below the height of the deck, and then everything will be happy. Yeah, so I need to make a few changes there. Austin says, glad I can diagnose your PCB schematic. Yes, thank you. Oh, Scott says, not allowed to end the stream until you bodge it now. Wagon Loads asks, can you rename the mode pin? Yes, I can. Dodgy! Good afternoon, Dodgy. All right. I think I am going to... I think I will possibly bodge this, and I will keep the stream going while I bodge it. But first I just want to have a quick look at what I need to bodge, because I may actually have a bit of a problem with this bodge. So we've got the clock here currently going to, so this is the output of the clock pin, and I need to have it going instead to, let's get rid of OpenKO for now, and we'll go back to just the two Testomatic revisions. I need to have it instead going to, where is it going to? Over there. Oh, it's right over there. Okay, so ideally what I would do is relocate the clock circuit from here and put it up here on the PCB, up in this area, where this rectangle that I'm highlighting. So I will move this and put it up here so that it gets closer to the clock pin. But for now, I'm just going to bodge it. All right, so what I need to do is I need to separate this clock pin from there and bodge it up to that pin up there. That's going to be easy. Now, what I'm more concerned about is the other two, because they're going to be connected to, one's going to be connected to a ground plane, and the other needs to be moved to a 3.3 volt rail, and the ground is going to go through in underneath the pad. Now, let's see what the deal is there. What's the dealio? So I want to take test PLL, no, mode, which is pin 31. All right, pin 31, I need to isolate this one. So this pin 31 needs to be isolated from ground, and it needs to be pulled. Hang on, while I'm talking about this, I'm just going to do this. Sudo halt, because I'm going to have to pull that PCB out of the chassis to make this bodge. And if I pour the polygon here, you will see that that pin is connected to the ground plane on the top of the PCB, both underneath the chip and like under the pin there and exposed on the pin, which means the only way I can pull this up is to remove the solder and bend. So the pin currently comes out of the chip down at an angle. I need to bend it up to isolate it from that ground plane. That's not too bad. I can do that. All right, now that I have a bit of a plan, getting this getting this out is actually going to take a little bit of work. Before I do that, muting for a second. Yumminess of iced coffee. So what I'm going to do is put that aside. This is powered up. The Pi is shut down, but we still have power on. So I'm just going to power that off and unplug that XT60 connector. Might as well turn off the lab supply at the same time. So what I need to do is rework on that chip in there. Ooh, yeah. I am wondering if I can do the rework without taking the PCB out, but I really don't think I can. I want to get this board sitting flat. Oh, this is going to be quite a disassembly job to get to it. Oh well, I think it has to be done. So USB out, power cable out. What I don't want to have to do is take apart the whole chassis. Oh, I may... Oh no, I can just take that off. That's okay. All right. Nothing for it. Just gotta do the needful, as they say. I have to take the touch screen off in order to get to the screws on this side of the mounting plate to remove the PCB from this vertical mounting plate. Oh, which reminds me, talking about all of these plates, I'm going to put all of the mechanical design in GitHub as well, so that other people can mess around with this, laser cut your own pieces, do your own modifications, whatever you like. All right, now I'll unplug HDMI without dropping the screen. And I'll remove, what else do I need to unplug? Oh, just the big IDC connector. Can I get that out? Might be easier to get it off this end. I'm going to unplug it from the Pi instead. And then it is a screwdriver job, because these are not hex heads. Putting this back in, I'm probably going to have to do something weird to hold the enclosure on its side. Otherwise all these little standoffs are going to fall out. Alright, so while I'm doing this mindless mechanical stuff, somebody tell me a story. Tell me what you're up to on this Father's Day today. Doing anything cool? Ah! Dropping stuff. What is going on? Do it on another one of the PCBs, asked Jack's Tech. Yeah, I don't have any others assembled. So far, I have only assembled one of these Testomatic boards because I wanted to validate the design. So yes, I could do it on another one, but I would have to actually assemble all of the other parts as well. And there we go. Oh, that wasn't too bad, getting it out. Getting it back in is going to be the interesting trick, because of supporting all of these little standoffs and things that are right all at the same time. And okay, so there's the chip. I need to isolate that pin from ground and link it to 3.3 volts. I need to isolate that output of the 48 megahertz oscillator. Let's move to the microscope. I think that'll be far more practical for this. There we go, yes. So this is just there. That's the mode pin. I need to isolate that from ground. This is the oscillator. 48 megahertz comes up here and it currently goes to that pin, and I need to jumper it across to one of these pins. So step one is going to be getting Oh. Getting our eyes on the prize and being able to see what's going on. Now, focus on screen is different to focus, oops, where are we? Yeah, focus on camera is different to focus through the eyepiece, but that's acceptable. Now, I need my dirty rework tweezers, the ones that have, where have they gone? Here they are. The ones that have flux and other rubbish on them. So what I'll do, which tip should I use? I think I'll go for the little bendy, pointy tip for this one. Clean it off in the tip cleaner. I'll try to avoid using flux and making a big mess. So I think I should be able to just heat it up and bend it up. That is my crude plan. Heat it and bend it, hopefully without breaking it off. Okay, is that separated? Let's find out. Yes. Okay, so that pin is now separated from the... Ooh. It was very close to breaking off then, I think. But it's now separated from the ground plane. And I need to connect that to 3.3 volts, which is somewhere. Maybe there. That might be a 3.3 volt point there. And one of these, I think that one, I need to connect across to here. And that I need to separate. So I'm going to isolate the 48 megahertz clock right here. And prevent it going into that EE clock. I don't even know what the EE clock pin is for. Prevent it going into there. And then, what will I do? Maybe about here. Scrape back some of that solder mask so I can put a bodge wire on. And this is this is super dodgy. A 48 megahertz clock is going to be going on a little bodge wire, waving around, flapping in the breeze. Not ideal. But hopefully it'll still work. It'll be functional. So now I need to find which pin am I connecting to. Oh, that goes to 3.3. Where? Which pin? So it needs to go into test PLL, which is pin 27. Oh, which I currently have pulled high. So test PLL, yeah. Okay, so I need to isolate pin 27, which is that one there. Okay, I need to pull that off. It's the third one across. Oh, and that is 3.3 volts there, so that's handy. All right, I've got access to that. Back to here. So that pin there is where I need to feed the 48 megahertz into. Oh, got to fix this focus. There we go. It's a little bit better. All right, so I need to isolate that from its pad as well. Now I'll try to do this one also without breaking off the pin. Because if I break off the pin, I suppose I can always just replace the IC. Come on. Lever it up. And up. Getting there. Come on, come on, come on. My technique here is not very good. I'm trying to be delicate because I do not want to break that pin off the chip. Is it free now? It appears to be free. It's a little bit hard to see in that vertical view, just looking straight down on it. Yeah, it is free. Okay, so I've got this, which is where I need to feed in the 48 megahertz. I've got this pin that now needs to go to 3.3 volts. I'll do that one first and then I'll bridge across the 48 megahertz. So I need, excuse me, I need some bodge wire. Bodge wire. Just searching for some bodge wire. I've got some wire wrap wire here somewhere, which would be suitable. Where is my little thing of wire wrap wire? Okay, just here. It's going to be short bodge wires. Oh, come on. I'm trying to strip the insulation off and it's just, it's just cutting the wire. All right. I know you can't see what's going on right now, but in just a second you will. Just tinning the ends of the wire. Normally I'd have the fume extractor running now, but it's noisy. So we've got, okay, so that is picking up 3.3 volts. And then I'm going to bend that wire back around into a U shape. Bending back around. And I'm going to connect it to this pin here, which previously was pulled to ground. Oh, that is a terrible solder job. Very yucky. Needs a bit of freshening up, bit of flux. It'll do. All right, so now we've got 3.3 volts going to that pin. Next, I need to bodge from there across to there, which will be the 48 megahertz clock. I need a short bodge wire for this. And once again, tin the wire. I really wish I could hear the chat, like a voice channel, a voice back channel or something would be cool. Hearing people's actual voices would be cool. All right, so 48 megahertz clock there. And yes, I'm making the clock bend 180 degrees. I hope the little clock signals don't get confused. Is that connected? I think it is. Oh, yeah. Oh, how bodgy is this? Alright, I'm going to zoom back out again so you can get an overall view of the bodginess. So we've got the bodge wire across the top there, moving that from ground to 3.3 volts. We've got the bodge wire across there, taking the 48 megahertz clock into the XPLL pin. Now, for this test, I actually don't need to physically mount everything again properly. I can just plug it in and see if it works. That might be the best thing to do. Although I do need to plug in the IDC cable. So I'll connect that 1 to 1. Pass that through here, because this is what is supplying power to the Raspberry Pi. And then this is the USB cable going to, I kind of do want to mount it because it's quite dodgy and I've got to get power plugged in anyway. All right, I'm going to try to mount this. Yeah, no I won't. I'll do it after the stream. You've already been waiting long enough. So I'll bodge in the power cable, plug in USB, and wink. I'm not even going to plug in the screen. I'm just going to power up the Pi without the screen. So I'll bring, this is power from my lab supply. And we'll turn it on. We'll see what happens. Okay, so the Pi should now be booting. And we will see if it comes around. What do I want? This. Okay. So I'll just give it a moment to finish booting, and then I'll try SSHing back in. Outside the box is I can see one of those screws shorting it out. Ooh! Good point. Thank you, Crispian. Yeah. Scott says the ones are pointier. Zeros can smoothly flow around corners. Oh, Austin says I should add solderable standoffs so I don't need nuts. That's a great idea. Yes, I really should do that because it's quite awkward. Yes. Okay. I am going to Vim to do solderable solder nuts on PCB to avoid standoffs. Yes. Okay. Now the thing is that might affect the front to back positioning of the connector and the PCB. I'll have to take that into consideration. But yeah, that is a cool idea. All right, SSHing in. And LSUSB. And we still don't have it. Okay. Paint on nuts to capture them. So it's outside the box. All right. The USB hub is still not appearing. What is the other end of that cable plugged into? So one of the questions is whether I have this. At the moment, this hub is plugged in on a USB-C cable going to. Okay, hang on. I'm going to switch cameras and explain. There are these 4 USB ports here on this end of the Pi. There is another USB-C port down here, which can be used for powering the Pi. And according to what I've been able to find out, that should also support USB 2.0, but maybe it doesn't. So this is currently a USB-C to C cable connected into that port. So let's try unplugging this cable, and instead, and I'm going to unplug that. So this is the this little dongle is the receiver for the barcode scanner. I'll unplug that, and I'll plug in instead, if I can get it in there, a USB-C cable. What do I need? I need a USB-A to USB-C. Will it fit? Will it fit? Which way over does it go? Other way, that way. So I'll try plugging it into this port instead, just in case that USB-C port on the Pi 4 does not work as a data connection, only as power, because that could also be an issue. All right, plug this in here, and come back to here. Let's do this again. Nope, still no port. Okay. Austin says plug into Mac. Yeah, that's a good point. I could try that. But then I would need to power it separately. Oh, Crispian says, used to use tamper paint after bolts in nuts, then nuts stayed in place for subsequent assembly. Oh, hang on. TUSB hub, it is there. Yes, Austin, you're right, it's there. I I just looked at it and I thought, oh yeah, it's still only four devices, so it's not there. But that's because I pulled out the keyboard dongle receiver thingy. Yes. Oh, okay. So now we have a working hub. Debug successful. Thank you, thank you. Oh, right. That makes me very happy. All right, we now have a working hub, and the bodge worked. Okay, so that was obviously a serious brain fart moment for me when doing the schematic for this. I really screwed this up. I don't know why I thought that EE clock, in fact I'm curious, I want to see what EE clock does in the 2046. EE clock, EECLK, yep, EECLK, there it is. EEPROM serial clock, it's got nothing to do with the system clock. EEPROM clock. Oh, I don't know. Okay, how about now? Yes, the battery went flat on the microphone that I'm wearing. So the receiver is still powered up, but the actual mic that I'm wearing went flat. So I've just turned on a I've just turned on the my other microphone, because I've got these little, what are they, Rode Wireless Go 2s, and I've got several of them. So I turned on another one that happens to be fully charged. Okay. Well, yeah, plug in the dead one before you forget, says Austin's Creations. Austin, you have saved me today with, again, with your insight into the USB stuff. So I have just plugged the other transmitter in. Yeah. Now, yes, as Cable Tie says, it is well and truly lunchtime. That's a feeling of satisfaction that now we have the hub working. Now, I haven't actually checked downstream ports, obviously, but the fact that upstream works and this hub is identifying itself, that is a very good sign. And I also need to investigate the EEPROM, why the EEPROM is not showing up. Yeah. All right. 12:40, so I'm at the 2-hour 40-minute mark. It is definitely well and truly time to stop. So, thank you for coming along on this wild journey of discovery and mishaps and mayhem. We got there partly. What I was expecting to do today and what I did today, totally different. I thought that what I would be doing is exercising the MCP 23017s and the ADCs and things and actually talking to them. But at least we can see them on the I2C bus, which means the rest of it is just a software problem, and that's easy, right? And we do have the hub verified, and we've got some fixes sorted out. So this is good progress. This is good progress. Okay, so Scott says, could bodge the EEPROM issue too? Yeah, I'm not even sure what the EEPROM issue is yet, though. That's going to take some more investigation. And thank you everybody for coming along. I am really quite hungry now, so I think I'm going to go and get myself some lunch. You should get yourself some lunch or some dinner or some breakfast or whatever is appropriate in your particular time zone / sleep cycle. And for those of you who are coming along, next week is barbecue week, so have a fantastic week in the meantime. And I will do some updates on the GitHub. I'm going to add the v2.1 design as well with these fixes. So be careful of the v2.0 that is currently there, because it has this balked USB hub design. I will put the v2.1 design there, and eventually I will get to putting up the mechanicals as well, so people can laser cut their own stuff. Wagonload says, your 3v3 bodge over a ground pad is a future magic smoke problem. Yeah, it definitely is. It definitely is. If that gets pushed down, yes, magic smoke. So I've got to be careful of my handling of the board with this bodge wire in place. Maybe slip something underneath as an insulator. Or put a dob of Loctite gel on it or something to keep it separated, because you've got to keep them separated. Okay, this is the longest goodbye of all time, but goodbye, and I will talk to you all really soon. Thanks. See ya.